Can't compete with everybody else talking.
Sorry, I
I'm
just
not trying to
recording.
compete with Joshua. Right, the California bearing ratio, the CBR test, is a test that was developed in California, I don't know when, but probably in the 1920s, 1930s. It's an empirical test, and it's just for comparing material that you might want to use in the sub-base of a road. So when you've excavated the line of the road, taken out all the topsoil to get down to the main subsoil, and then what you would want to do is you set out all your levels, and then you'd want to put on here basically a foundation layer, which is called the sub-base. It's using unbound material, put it in, roll it, compact it. Okay? Now, what you'd really like to do is to be able to put back what you've already dug out.
Yeah.
Especially if you're having to dig cuttings and things and make embankments, you want to use it again. So what you need to be able to do is you need to be able to find out whether that soil is suitable. And this is what the California bearing ratio test is all about. It's finding out what is the resistance to deformation of a material that you might want to use for the sub-base of a road. In the UK, there is some specification for sub-base material that you can buy in, and it's MOT type 124. Now this material that I've already prepared here, you need a lab coat. Okay, so the material has already been prepared, right, and it's been placed in there. And the way I prepared it is that first of all I've sieved it to remove everything bigger than 20 millimeters, and then it's been compacted in these molds. Okay, compacted using a 2.5 kilogram rammer or hammer that drops onto the soil 62 times, and you fill it in 3 different layers. And you've got the drop is 300 millimeters, and it's all done by machine. I don't have to do it. Just stick in the machine and switch it on. Okay, and that machine is over in the geotechnics side. Right, so before we fill in our molds, there's some things that we need to know, and I've actually got that information for you already. For instance, we need to know what is the depth of the mould. And if you have a look at the handout that you've had, you'll see that somewhere you have this table. And you need to know what the diameter and the depth of the mould is. Like I need to restate the one. $152. Okay. And the other bit of information you need to know is what is the actual weight of the mould in its base. And I have it there, 5635 grams or 5.635 kilograms. So that should go in all of these spaces here. There's one other bit of information we need to know, and that is, I'm going to take that off now, is I need to know what is the weight of the whole thing including the soil. So if somebody like put it on there and weigh it.
They can trade on it. You don't. If you work, you get the money. They can trade on it. That's how it is. And they can trade on it.
Right?
10.34.
You all made note of that?
Yeah.
Right, now I need to sort of have a bit of clear working area just here. Right, so now we're going to put it into the press machine. Right now, and this is just a standard compression test rig. Okay? And what we do is we adapt it for various things. You can use it for triaxial tests, you can use it for CBR tests, you can use it for timber tests you did down there. All you do is you just put the appropriate thing in there to do the job. So it's now been set up with the CBR. take the sample off there.
What are we trying to do?
In here. Center it as best we can.
You are ready.
The next thing I'm going to do is I'm going to have these surcharge discs. I'll put them on and then I'll explain to you what they're all about. Oh, actually, I don't put those on just yet. I'll close the gavel first of all. No entry fast, right.
There is not.
Right. Okay, so I put the surcharge. Right, surcharge discs are in place. Okay. So the surcharge discs. Surcharge discs are there to represent the material that goes on top of the subbase. Because the subbase is the unbound layer that's compacted to make the foundation. Then on top of that you will usually put a bound base layer of some sort. Yeah. So it could be cement bound, bitumen bound. And that will go on top. And then on top of that you'll have your wearing course. Right, in a road structure. In fact, sometimes for the hard, roads that need to be really hard wearing, like in a motorway or a landing strip in an airfield, those sort of pavements, they often have more than layers than that. Right, but that's basically what you really need to do. So when you're designing the road, what you've got to take into account is instead of having this heavy stuff on top. Yeah, and that's what this surcharge is for. And this is what you are going to need to know, because if you are the engineer who's asking for me, the technician, to do the test, I'm not going to decide know what the surcharge is going to be. You as the engineer, you know how many layers, and you should be able to work out the mass per unit area of that material, and you should be able to tell me what mass of surcharge I need to put on top of the specimen. Okay? So that's where this sort of thing comes in. I need to know that information. So you've got the surcharge.
Does it matter that the surcharge doesn't fully cover the top base of the side?
Yeah, it doesn't matter, no. It's just that's the standard size of surcharge. Standard size of mold. So it doesn't matter, that's just the standard size that's there on top. Right, now then. So we've got that in place. So the next thing I need to do right, yes. So apply the seating force. See, that doesn't
Work with us. Okay, and you have to do what you call. Okay. Yeah, work with us. Okay.
Who's trying to wreck my equipment?
You can turn. Okay.
Why adjusting this?
It's not quite straight. He's a bit better now than he was. It's not perfect, but it's better. Righto. So we know that it wasn't touching, so we know that this should be zero load up here. I'm going to turn this to run, and it's 1 millimetre per minute, which is correct. so I can start applying the seating force. Now the seating force, I'm guessing, is 250 newtons, because depending upon the value of the CBR, you determine what the seating force should be. Now I haven't done the test, so I don't know what it is. Yeah. So whenever you are actually doing the CBR test, you really need to supply at least one extra specimen that's needed, because somebody's, for each type of material, because the technician may guess the wrong seating force. Okay, so you'll need to be able to redo it again. Because once you've done it, even if it's the wrong seating force, when you've done it, it's not a very accurate result, but at least it gives you a good idea of what the seating force should be, because you have a reasonable idea what CBR is, so you can use the right one. So I'm assuming that this is quite a strong material, because it is a rotor-based material, it's not a soft clay, and so I'm going for the higher seating force of 250 newtons. And I know that 250 newtons is going to be 14 divisions on there, because there's one other bit of information you haven't got at the moment. It's a low ring calibration, and if you look on the side here, it says that it's 17.985 newtons per division. So I divided 250 by 18, round up a bit, and came out with 14 divisions seating force.
Kilonewtons per division, yeah?
Pardon?
Kilonewtons per division.
Newton. So I can now get the seating force on. So I press that button and see if we get the load applied. It's touching now. See it moving. I don't think you're going to see much just down there. Righto, so we've reached 14, it's falling back now because it's moving a little bit underneath the measuring. So now I need to set this to 0. At the moment it's not quite 0, so I'm going to have to try. This is read 0. Okay, so that was in 0. You now put this back to 0, and we are now ready to start the test. So we should have, those of you who are recording it, you should have this bit of information, that bit, that bit, that bit, that bit in there, this bit in bold you've got to calculate, and so we're now on this area here. So penetration of the plunger at 0. So this is 0 because this is going to measure the penetration of the plunger. So the force gauge reading is going to be 0 because I've zeroed it up there. So what you're going to do now is that somebody's going to have to watch this dial, and every time it moves 25, which will be 0.25 millimeters, so 25 you take a reading, 50 take a reading, 75 take a reading, 0, and then so on all the way around continuously. Filling this in, so you take the readings from this one up here. So that's probably going to be the job for the tallest chap here, because it's easier to see if you're the right height to get more accurate.
So does it go to 100 and 200? It goes down?
Yeah. Once it goes past 0, it's 100 and something, and so on. Okay? So what you need to do is, somebody here needs to be watching this. As soon as it gets to 25, shout out, somebody else reads that, and then they can shout out to whoever's scribing so that they can write down the result, and you carry on until you get to the end. So as soon as you get to the end here at 7.5, right, you need to hit the red button and stop it. So when you're ready to start, you hit this button to start, and from that minute onwards you're going to start taking the readings, and then when it gets to 7.5 millimeters, on this end here, hit that one to stop. So I'll leave it here.
I'll read this one. Hold on, stop it now, yeah?